Um, so today I'm gonna give you a little bit overview of some recent data and results that we have got about neural representations of valence from visual and auditory modalities. So whether we're happy, angry, sad, etc., emotion matters to us because emotions can actually inform us why things matter to us. So it's one of the most fundamental aspects of being a person. But emotion is also very complex. So there are debates about how many emotions there are, whether it's 5, 6, or 7, or there's some other social emotions like guilty, shame, etc. So from a dimensional point of view, the dimensional theory provides a simplified version theory to categorize emotion, which is that there are two basic elements of emotion. One is valence from negative to positive, and the other is arousal from low to high. So basically, the literature have shown that if you ask somebody how do they feel, their description of their feelings in general would be categorized into the two dimensions, valence and arousal. And like, I feel very happy today. So basically, the words that you use are mostly about valence and arousal. And so these are basic elements of in our emotions in everyday life. And within the two dimensions, valence is more important than arousal. So it's basically taken as the most important building block of emotion. So today I'm gonna talk about is mostly focused on the neural data. So mostly it's about how does our brain, create emotion, and why, is there different systems for processing emotion from what we say, and or there, the same system for processing the emotions of what we see over here. So for example, when you see a cute cat, so you basically receive the signals from both video and audition. So you can see the cute cat and you can hear some cute sounds, and you basically feel the sense, feel the experience of pleasure. So in that case, how would the visual affective signals and auditory affective signals represented in the brain? That's the question that's very important for understanding emotion processing. So the traditional view of emotion suggests that there might be a common, which is called modality general affective system. So we might only have one single hedonic system for processing affective signals independent of modalities. So which basically include a bunch of limbic brain areas, such as some subcortical structure like amygdala, hippocampus, thalamus, and also there are some orbitofrontal and temporal pole brain areas. That might be this common subbrain region might be actually important for emotion processing, regardless of where the emotion signals come from. However, some recent data have shown that actually there are also modality-specific brain systems. So instead of using a common set of brain, system for processing affective signals, there are specific, system for relevant for processing either visual signals or auditory signals. But there are different, results. Basically, some of the data shows that the modality-specific representations might in the perceptual cortices. So instead of the high-order cortex, the perceptual cortices might has the ability to represent the emotions from specific modality. So, for example, it could be this study, Chicago study, shows that the visual and gustatory representations might be in specific perceptual cortices like ventral temporal visual-related perceptual area, or some other gustatory-related anterior insular brain regions. So, however, the other possibility is that there might be some high-order cortices that are visual or auditory specific, for example, or modality specific in general. For example, the Dannenberg paper shows that the different parts, different subregions of the prefrontal cortex might actually involved in a visual or olfactory valence processing, respectively. So basically, there are questions about, in general, about are there common and distinct new representations of valence processing from visual and auditory modalities? And also, it's not clear what the brain regions are commonly involved in valence processing independent of modality, and what are the visual or auditory specific brain regions. So, so first of all, I'm going to present some data to examine in the same study to examine the modality general and modality specific representations of valence from visual and auditory modalities. So to examine this question, we collected some fMRI data from MCBI, my course and center. Of course, it's before COVID, and so we have 21 subjects, and so within the 21 subjects, we have 14 women, and it's young adults. So in this experiment, we are using the typical set of stimuli from our lab, which I say typical because it's being used in multiple studies, and it's been a long-term development process. And basically, these are naturalistic video and instrumental music stimuli. And I can show you some of the, oops. Never mind. So I think it works when it's not presentation mode, but it's just some cues dancing. And here's some of the music stimuli in case it's too loud. So basically, we use this kind of a prior normed affective videos and music stimuli. The reason that we use it is because we try to be more kind of naturalistic. Because a typical study that used in prior literature is a typical stimuli that used in prior literature is about the static pictures mostly and words or something like that. So, in order to examine actually in kind of to account for the more ecological validity and more kind of naturalistic, it's not exactly totally naturalistic, but it's more naturalistic compared to the static pictures. So we're using this stimuli with arousal balanced, and we manipulate the valence in this experiment. So we have two conditions specifically. So we have the visual positive or negative videos or music and videos, and also the auditory, basically the positive and negative music. So we have 2 by 2 and reach into the 4 different combinations. So the reason that we use this design is because in that way we can say by comparing different combinations, we can say what's the what basically the different models can be tested. So what are the brain areas that are specific to sensitive to the alteration in specific valence in each of the modality. So in the specific task is so in the scanner we have the subject to basically, it's very simple. It's a slow event related design, and let the subject to watch the specific presentation of the stimuli. And after the presentation of the stimulus, there's a 7-second inter-trial interval. And we also have a catch-all in the scanner task because just to keep the participant focused in the scanner. And the catch-all basically after the presentation of the stimulus, we ask them to, how do they feel overall? It's a 2-button response, basically overall positive or overall negative after the presentation of the stimulus. And after the in-scanner task, we have the post-scanner experiment. So the post-scanner experiment is a behavioral experiment that participants sitting in front of a computer and read all the same stimuli that already been presented in the fMRI experiment. And the reason that we do the post-scanner experiment is to basically to get the valence and arousal ratings. And so we can validate our manipulation of this experiment, as well as we can get the individualized valence and arousal ratings for each person. And so we can use this kind of a individualized valence and arousal ratings to derive the empirical valence model. Yeah, so if there are any questions, just stop me, any moment in the middle of the talk. So just in case that I didn't make something clear.
So the subject, I mean, the participants are divided, it's between subjects. So the experimental catch trial.
Oh, the catch trial. Yeah. So so the do you mean there is divided by between subjects?
Yeah.
Oh, it's actually the same set, essentially the same set of a program that used across subjects. So it's actually not different across subjects. So yeah, they're all basically seeing the same catch-all. So it's actually not divided between subjects.
And then only experimental trial, you check self-paced ratings about Valence and arousal, not catch trial.
Oh, I see. Yeah. So for the post scanner, exactly. Yeah. So we only check we do not check the catch-alls. Exactly. Because we are not interested in the catch-alls, it just keeps their attention. And we actually do not include them into analysis for the catch-all. Yeah. Okay, does that make sense?
Mm-hmm.
All right, yeah. All right, so we use a representational similarity analysis, try to test different models, because this approach can actually capture the representational geometry of different models. So basically, we have specific models, conceptual models that we want to test. So the modality general model are assuming that there is a common neural system for processing valence regardless of modalities, and visual specific is kind of the visual specific valence model and auditory specific valence model. And also we have an empirical model, which is derived from the post-scanner task that we have individualized valence ratings. For each of the stimulus, and then we can derive an empirical valence model. So basically the idea is that we use the representational similarity analysis. We want to capture where in the brain I actually fit the modality general model better, and where the brain actually fit the visual specific model or auditory specific model. So here is a conceptual model because it's actually derived based on a conceptual understanding. So basically the modality general model, for example, it should be able to tell the difference between visual positive, auditory negative with the visual positive, auditory positive, because there's a difference of valence in the auditory modality. So the modality general model should be able to tell this difference. However, the modality general model cannot tell the difference between visual negative auditory positive versus visual positive auditory negative, because the modality general model does not differentiate where the valence comes from. So basically you assign a 0 here because they are essentially similar. They are the same thing. So because the modality general model cannot tell, so it's assigned a 0. But if it's a 1, and then it means that modality general model can tell the difference between the conditions. So actually, I show here is a 4x4 matrix, but in our real analysis, we also have 2 repetitions. So within each condition, so we basically have an 8x8 matrix that are used for analysis. So this is for modality general model, but for the other visual specific and auditory specific model, we have essentially the same idea. For example, the visual specific model, for this one is the visual positive, auditory negative versus visual positive, auditory positive. So the visual specific model cannot tell the difference because visual valence are the same here, and so there's only a difference in auditory modality. So visual specific model shouldn't be able to tell, so there's a 0 here. So yeah, essentially that's the idea. I don't know if you guys can see my mouse movement. So if not, and then it's a little bit difficult. Okay, good. So and empirical valence model, basically we got the individual valence ratings for each stimuli, and then we can basically calculate the Euclidean pairwise Euclidean distance between different conditions, and then we can get the empirical valence model, and then we can derive an empirical valence model for each subject specifically. But the conceptual model are all the same for all the subjects. So when applying the representational similarity analysis, we basically use the brain, some data from the brain. For example, if it's ROI analysis, we're gonna take a bunch of voxels, for example, from the supratemporal cortex. And then we take out these voxels, and then we calculate the neural dissimilarity matrix. So the dissimilarity matrix that we used here, the distance measure is the cross-validated Mahalovitz distance, which is basically a linear discriminant t-value. Basically, we train on, so in the scanner, we have 3 sessions. We train on 2 sessions and test it on the remaining session. Basically, get the linear distribution t-value. So we use the vectorized lower triangle vectorized new discriminant matrix to correlate with the conceptual model matrix, which is each of the four models. So in that way, we can say, does a specific ROI actually significantly correlate with the which of the model, or where in the brain actually fit each of the model the best? So this is the essential idea of the analysis procedure. All right, so so we did two types of analysis. First of all is the ROI-based representational similarity analysis. So and then we did a data-driven searchlight analysis. So the ROI-based analysis is based on the conceptually derived region of interest. So there are several regions of interest that we are focused on here. Basically, there are primary visual cortex, primary auditory cortex, and supratemporal cortex, and orbital frontal cortex, and thalamus, and pregenual anterior cingulate. So, so these are the brain regions that are related to, some of them are typical regions in the limbic system. Some of them are brain regions that have been identified to be related to either modality general or visual auditory, modality specific processing. So we tested each of the brain regions, and so here the result shows that for the modality general brain region after FDR correction, their supratemporal cortex is significantly related to modality general brain region. And basically our supratemporal cortex and orbital frontal are mostly correlated with modality general, but not the others, but only supratemporal is significant. And then for visual specific, the most significant correlated with is the brain area is the primary visual cortex, which makes sense. It will kind of support the engagement of perceptual cortices in modality specific valence. And also we found that the supratemporal cortex is correlated mostly with the auditory specific model. So this also kind of suggesting there's a kind of a perceptual engagement, because the supratemporal cortex is actually is a pretty large brain region that has secondary auditory cortices as well. So so it could be interpreted by the perceptual engagement, or there are also literature suggesting some of the modality general role of the supratemporal cortex. So which would support both the engagement of the modality general and auditory specific in this brain region. So for empirical valence model, we didn't actually found any significant with any of the ROIs, but we did find that there's basically the primary visual and auditory are mostly related, but these are not significant. So shouldn't be interpreted too much. So here's the ROI analysis. Basically, we get an idea about the possible support the possible hypothesis that the modality specific representations and the modality general representations, and also the modality specific representations are kind of in the perceptual cortices here showing the ROI analysis. But the ROI really has some limitation because it can be biased by our basically conceptualization. So we did the searchlight analysis. So basically the searchlight analysis is just a search cube that we use a 5x5x5 voxel search cube and search around the brain and do exactly the same analysis across the whole brain. And then we account for the multiple comparison correction and using some permutation test. And so here the result shows the conceptual models, the results are different models. So the green color is a visual specific model, and blue color is auditory specific model, and red color is a modality general model. So first of all, you can say the visual specific, which is the green color, is generally more posterior represented compared to the blue color, which is auditory specific model. So and there are kind of some of the visual related brain area are involved in the visual specific representation. And also there's some kind of a precuneus and precentral postcentral area that are also involved. And also the auditory representations are mostly kind of a very big cluster. The biggest cluster is in the supratemporal cortex, which makes sense because there are lots of auditory cortices in the basically supratemporal cortex. So and also we found some of the representation of modality general as well in the supratemporal. As you can see in the red color here, so this is kind of in line with our analysis as well as some of the prior literature suggesting the role of supratemporal cortex in representing valence from each of the modalities. And also we got some of the medial prefrontal cortex that actually has the engagement of all of the three models, somewhat engagement overlapped here. This can support the argument that the modality-specific representations might also be in the high order cortices in addition to the perceptual cortices like the prefrontal cortex. So one of the studies shows that the visual representations might be a more kind of a dorsal area of the prefrontal cortex, but the olfactory might be more in the ventral part of the prefrontal cortex. So it's suggesting that here we found is that it's like they're very close. They are mostly the dorsal part of the prefrontal cortex for visual and auditory specific processing, but they are kind of a somewhere different, but it's very, very close actually. And then here is showing the empirical valence model, which is basically derived based on the individualized valence ratings for each subject. And then we use that to derive the empirical valence model that I showed in previous slide. And then we do this, apply the same analysis procedure. And here shows some of the brain activations related to empirical valence model. So this model has an advantage because it's based on individualized valence ratings, because we cannot assume actually everyone has the same affective feelings upon they say the same stimuli, because there might be different feelings saying the same thing. So so the empirical valence model can really account for that. So that's the advantage of this, and it shows some of the similar brain area in the prefrontal cortex and the precuneus and the supratemporal brain region and anterior insular brain regions. So basically, this data shows overall there are both common and distinct new representations for valence from visual and auditory modalities, and modality general brain regions. Here we show that there's different types of modality general brain region like supratemporal, like medial prefrontal cortex. But importantly here is that the supratemporal cortex that we identified is an important brain region, modality general brain region for visual and auditory process. But there are some prior literature shows that the modality general brain region might differ actually when it's a modality general between different modalities. For example, it's between visual olfactory, visual gustatory. So it sort of makes sense that the supratemporal cortex come out for visual and auditory, because some of the literature shows that supratemporal is actually your audiovisual integration area. So here is also, our study also confirms that the role of this brain region in representing modality general valence. And modality specific valence representations we found are in both perceptual. Some of them are secondary perceptual cortices, and also are in high order cortices like prefrontal cortex. So these results basically suggesting that how does our brain actually represent the emotions from visual and auditory modalities. So it seems like we have a very flexible set of a brain area that a system that are used when we are processing signals from what we see and what we hear. And there are some common and also some distinct that can can be used to better represent the emotions. Okay, so next we want to ask a question is, so in addition to focus on the modality general and modality specific, we want to focus on how does our brain actually combine the visual and auditory signals. So the next analysis that I'm going to show is basically focus on the audiovisual valence congruence. So in our real life, there are many situations that, for example, when I hear pleasant music, at the same time I see a cockroach, approaching me. So in that case, there's a valence congruence across what I see and what I hear. So this kind of a situation can happen in lots of times, and it's important to know, like, how does our brain actually can detect this kind of incongruence, and what brain regions are important sort of to combine the source, from what we see and what we hear. So the first question we want to ask is a more kind of a general, is it able to predict the affective congruence in individual trials of a new subject based on fMRI data? And then we want to further ask the question is that what are the difference between the brain representations of valence congruence and the representations of valence itself? Because here is actually a meta-analysis results that we show here is that summarizing all the previous studies involved in audiovisual affective processing. So basically these studies are mostly using a contrast, is the interaction contrast, which can basically identify the audiovisual combination, audiovisual affective combination brain region. So the brain region that are responsible for integrating visual and auditory affective signals are basically posterior, supratemporal, thalamus, amygdala. So as you can see, actually these kind of brain regions are very similar to the emotion brain regions, right? So it's kind of difficult to tell whether the brain regions specifically are responsible for valence processing per se, or are responsible for integrating the visual and auditory information. So actually to tell the difference, we want to examine is that what are the brain regions that are both responsible for valence congruence, which kind of a sort of a combining visual and auditory, as well as what are the brain regions, so that to compare to the brain regions that are representing valence. So to answer the question, first of all, we want to see whether we can actually identify on a new participant, to identify the individual on individual trials, they're positive or negative, or congruent or incongruent. So to answer this question, we did a whole brain classification analysis. So basically we train on the brain data. So it's kind of a supervised learning algorithm that we basically have the labels for all the positive and negative and the congruent or incongruent, and then we train on the subjects and test on the individual trials on the new subject. So if we are able to test, and then we can say that that the brain are actually informative to detect the valence and also the congruence. So indeed, we do find that we can successfully predict the valence congruence across visual and auditory modalities. As you can see, the accuracy is 72%, and also we are able to detect the valence, which is 87%. And here show the ROC curves, which is well above the chance, and so the area under the curve is reasonable. So so basically, this analysis, we got the idea is that we are able to actually classify on the new subject to predict, basically based on their brain data, to predict what they say are positive or negative, or congruent or incongruent. And the next we want to ask is where the brain representations are, basically in our brain, actually locally. So to answer the question, we did a data-driven search height analysis. It's very similar to the ISA search height analysis. Basically, we use a search cube to search around the brain, and we are basically doing the same type of a classification analysis. It's just we are doing a search cube, 5 by 5 by 5 voxel search cube to search around the brain and get the accuracy at each cube, the center of the cube. And then what we found is that the group analysis results shows a bunch of brain area, including inferior frontal, supratemporal, and anterior cingulate precuneus are responsible for the valence congruence. And there are a bunch of brain regions, supertemporal, precuneus, so involved in the valence. So when we do a conjunction analysis to say what are the brain areas that are involved in both valence processing as well as congruence processing, we found a brain region including supertemporal, mostly posterior supertemporal, and anterior cingulate are the brain regions that are responsible for both valence processing and congruence. So how to interpret this data? So basically we are, so we can think of that this brain region basically have multiple roles in when we actually processing signals from multiple modalities. So first of all, it can be the supertemporal cortex can integrate the audiovisual signals in general. So here is showing a figure from John Draver. So basically summarizing different models for audiovisual integration. As you can see, for the audiovisual, there's a model that suggesting that supertemporal cortex, mostly posterior supertemporal cortex, are important for integrating visual and auditory signals in general. So so it could be that the supertemporal cortex here, we identify here, is basically involved in integrating visual and auditory signals. And also, we notice the anterior cingulate brain region is frequently involved in valence processing, but also the literature showing it's involved in cognitive control as well as conflict monitoring. So, so because we are actually examining the congruence between the two modalities, so it could be the role of it here is actually detecting the conflict. So if there's a conflict, so because we are applying the really as an MAPA analysis, so it's non-directional, so we'll not be able to tell whether it's actually a congruence or it's incongruent larger than congruent or congruent larger than incongruent. But this analysis basically give us some idea about what are the brain regions actually are most important in audiovisual affective processing. So these are brain regions that are involved that might have multiple roles in processing affective signals in the audiovisual setting. So basically, the idea is that we got the results is showing that it's possible to predict affective congruence in individual trials of new participants based on fMRI data. And the ACC and STC might have dual roles in processing audiovisual valence signals, both kind of involved in the audiovisual combination as well as in valence processing per se. So so this data basically give us, in addition to the modality general and modality specific brain region representations, we also, this data answer a further question about what are the brain region kind of involved in combining or detecting the congruence from visual and auditory modalities. But these are just the fMRI data. So, the next question we want to answer is using some EEG data to examine the time course of audiovisual affective processing. Because there are different models of audiovisual valence processing, so it could be a early processing model, which is that actually it does not require some high order cortex. It could be just some perceptual cortex or primary cortex. There's some crosstalk between the cortices, and then it occurs very early. Or it could be involved in some secondary cortices or some integration, high order integration region or some other coefficient network brain region. So if it's an early crosstalk between the sensory or perceptual cortices, and then it should occur in the time course very early. But if it's late, and then using the ERP, we should be able, or EEG, we should be able to tell whether there's a more in line with a late model. So their previous literature have focused on the neural oscillations, and this is a summary of the previous literature examining the audiovisual affective processing, focused on the time frequency analysis of EEG data. So most of the literature are using a comparison between the audiovisual versus the sum of a unimodal. This approach is basically suggested to can identify the brain regions that are involved in combining visual and auditory signals. So what they found is a bunch of frequency bands might be related to audiovisual affective processing, such as alpha, beta, theta, and delta. It's mostly a low frequency band, but there are also some high frequency identified by several MEG study. So to answer this question, to further answer the question about, so basically this literature have several questions that have not answered. So first of all is they are mostly focused on is the total power, which does not differentiate the evoked power and induced power. So it's especially very important to examine induced power, especially the naturalistic dynamic stimuli used, because the activity might not necessarily time locked to the stimulus onset. So it can be a phase independent power. So, secondly, it's not clear whether there is a difference of the audiovisual integration depending on different emotional content. So mostly the analysis the previous study do is to average across different, they usually use discrete emotions such as happy and sad. So they just average happy and sad conditions and comparing audiovisual versus the sum or unimodal. So in that way, it's not possible to examine, it's still not clear to examine whether the audiovisual integration would differ depending on different emotional content. So to answer the question, we reanalyzed some previous data. So in that data, we have 24 subjects and it's young adult subjects, and we have exactly the same stimuli. So that I showed you before. So basically naturalistic videos and music. So for the stimuli, we basically manipulate valence. So we have positive, neutral, and negative conditions. So this time we have neutral condition as well. So because we want to actually answer the question about emotional content, it will differ, the neural oscillation will differ depending on emotional content. So basically we are balancing on arousal and only manipulate valence, and we presented the stimulus and asked the valence arousal ratings after the presentation of the stimulus with the EEG recorded. So basically first of all, we want to ask a question is, we want to use the interaction comparison that the previous study used. Basically, for each of the valence condition, we use a contrast between audiovisual versus the sum unimodal. And we examine the evoked power and induced power respectively. So here, as you can see, the results of the time frequency analysis. So for positive, neutral, and negative condition respectively, the audiovisual versus the sum unimodal identified or sub-additive theta activity at the very early temporal stages for evoked power, and it's mostly frontal-central distributed for that theta activity. And we also identified induced power, which is a long-lasting induced power activity. Basically, there's a delta activity as well as a beta activity. So delta activity is really widespread across the whole scalp. There's no really center distribution, but the beta activity is mostly frontal-central distributed. And so this kind of give us some idea about the neural oscillations that are related to audiovisual integration on different emotional content. So but we didn't actually find an interaction between the valence and the audiovisual integration comparison. But when we look carefully at closely at the evoked theta activity, we notice that actually, as you can see, this is a positive for each the data for each individual, and this is a neutral with the data for each individual. So basically, we are comparing audiovisual versus the sum unimodal. So for positive, neutral, and negative respectively. So you can see actually the effects are much larger for the positive and neutral compared to the negative. And we did a statistics analysis, which is a variation of principal component analysis with the variance across subjects accounted for. And then you can say actually there is a clearly distinction based on the statistics analysis that there is a separation between different valence conditions. So it suggests that the subadditive theta activity might actually can differ, depending on different emotional content. The induced delta activity, we found the induced delta is really kind of start to increase since the stimulus onset, and then in the middle achieve the max and then start to decrease. So the induced delta activity is really has been identified in previous literature related to reward processing as well as silence detection. So in our study, this mostly looks like it's a dynamic process in the involved in the audiovisual affective processing, and is kind of related to arousal in the first when we first look at the data, because it starts to increase and then decrease. But when we look at the individual, do the correlation between the arousal readings that we got with the inducer delta, we didn't actually find any significant correlation. But this can be interpreted. This is interesting, and it's totally different from the subaddictive theta activity, which is kind of early in the temporal stages. It's kind of a stimulus evoked activity, early integration maybe process here. And for the beta activity, we found that it's slowly increased towards the end of the presentation of the stimulus. And the beta activity in prior literature has been shown to related to the sensory motor processing. So we speculate that this activity actually might be involved in embodied simulation process in the emotion processing. So which is kind of also related to the sensory motor processing. Corresponding to the fMRI data is that some of the motor precentral or postcentral cortices, sensory motor cortices, might be actually representing induced beta activity. But we didn't actually, we don't have the data now to actually directly compare the EEG and fMRI data. But yeah, so here some of them are just speculations of different activity. So in summary, so what we got is that there is a visual and auditory affective cues might combine in multiple stages. So they have both early stage processing as well as late stage processing. And the early stage is time locked to the stimulus onset. And the late stage processing is more phase independent dynamic process, mostly the delta and beta activity. All right, so next I'm gonna present is really some fresh data. So luckily we got some usable. We got some data from ABC project. Due to COVID, due to COVID, it's difficult to get some data. So it's really good to have some data to analyze. So I'm gonna show you some very preliminary results from the analysis of the ABC data, the aging brain cohort data that we got. So the question that we focus on here is about the valence representations, new representation of valence in aging populations. So basically, it's larger than 60 years old. Yeah. So so why we are interested in that is because so there is some literature have shown that there is a difference in elder population compared to young population. Basically, there is a older population can experience greater positive effect and lower, greater lower arousal. And also, this study shows that the younger and older adults have different new representations. So this is a meta-analysis study. They compare the young and older, and they found that the young adults compared to older adults have some of the more activation in the amygdala, some of the subcortical brain region, and older compared to younger have some of the activation in the prefrontal area mostly. And so this is very interesting because why this kind of related to why there's a kind of a positivity bias in older population. So how does our brain actually involved in in this phenomenon? So but most of the previous studies are focused on is not that naturalistic stimuli. So so here we are focused on is from using the ABC data, which is a kind of a more naturalistic. It's not that, but naturalistic, but it's still experimental setting, but it's more naturalistic compared to some of the typical stimuli used in prior literature. So basically we are in this experiment, we have, so basically the ABC, the data have is to, there are some narratives. So there are 60 minutes English passage. So the participants are basically older populations, 60 to 80 years old. And they basically listen the passage in the scanner. And So we got some more data, but I only show here is 26 subjects because we only got the ratings for each of the passage for 26 subjects data. So so I'm gonna only show some very preliminary and fresh data. And if you have some thoughts on it, please let me know, because it's gonna help us to analyze the data better maybe. So here is basically the presentation of the experimental setting from Nick. So it's basically there's foreign language 50 seconds, and there's 8 seconds fixation, and then it's 6 seconds English passage, and then some foreign language fixation followed. So what we do is that we so first of all we got the 6 minutes board data, and what we want to do is to first of all to segment the 6-minute passage. And so because there could be different Valence ratings, that different feelings along listening the narratives. So what we want to do is to gather their feeling ratings after each segment. So we trained basically 4 independent researchers to segment the passage first, and then we have the 4 independent researchers to rate the passage. So basically they rate on valence and arousal for each of the segment after the presentation of each of the segments of the passage. So we obtained the valence and arousal ratings for 13 passages. They are altogether 24 passages. So so that's why I'm gonna show just part of the data, because we only get just half of the passage ratings. So here I'm gonna show you is, first of all, is some of the example valence ratings. So so basically the figure shows us 3 example valence ratings from 3 different passages. So for this passage, Alice and Age Mother, as you can see, the x-axis is the passage segments. So we altogether have from from 1 to 50 or 150 passage. And then we got the valence rating for each of the segments, and the different color shows the 4 independent raters. As you can see, in general, it's very consistent across different raters. So it's very consistent across all the passages. But here I just show you some of the examples. And also we got the here showing the arousal ratings for 4 different raters for 3 example passage. So arousal ratings are in general less consistent compared to the valence ratings. It's kind of but in general, it's still pretty much consistent across different raters. So we're gonna use is the valence and arousal ratings and average across different raters, and so that we can use these ratings to identify their board activity, where in the brain are kind of related to the valence dynamic change in listening the narratives. So basically, first of all, we do is a first level fixed effects model. So for each subject, we basically have a dependent variable is the board data. So so here showing just fake data. So one voxel board data. So we have, for example, 1 to 150 segments. So we basically have valence ratings along the listening the narratives. And also we have the board data from the first TR to the end of the TR. So, and then board data is a dependent variable, and then we have the valence arousal as a predictor, and also some confounds variables. So basically we can get the beta estimates at each voxel for valence and arousal. So we mostly focus on valence here, just to include arousal to account for the possible confounds of arousal. So, and then we are focused on the second level model is there to average across subjects. So there are different ways to account for the second level model because notice that we have one thing is that the same passage can actually have different subjects. So different subjects might have actually listened to the same narratives. So they're not totally independent across all the subjects. So there are some group structure across all the subjects. So that's why it's kind of important to account for the group structure. So across different subjects. So to account for that, we can fit a random intercept model to assuming that there are basically different intercept for different groups, or we can fit a random slope model to assuming that there are different basically relationships between predictor and dependent variable for different groups. So, so what we got here is showing you is the whole brain map of random intercept model and a random intercept plus random slope model. So here's a fixed effects beta map for the Valence. So as you can see, the scale is from 1 to 4. And so here, notice that, so I didn't actually do the multiple comparison corrections yet. So here is just really descriptive. We are now just running the permutation test. So we haven't got the results, but was here basically showing you some general idea where the largest, strongest valence related brain region. And it's interesting is that there are some primary sensory causes kind of are involved actually in the valence representation, and also some cortical structures like thalamus are involved in the valence processing. And the random slope and random intercept model compared to random intercept model, they're pretty much very similar, but there is somewhat difference. Like here, random slope model have stronger, here representations for the supratemporal cortex. And it sort of makes sense. Somewhat it's interesting that to say it's a primary auditory and some secondary auditory as well as primary visual cortex actually are related to the valence, dynamic valence change when they listen to the narratives in the older adults. But really, I don't want to make any, interpretation to speculation too much, but because it's not really a threshold data yet. But yeah, so overall, so that's I would love to discuss with you some of the results if you have some thoughts on it. But yeah, that's the really preliminary results that we got. Yeah, so finally, I want to thank my collaborators on the data that I present, and also to thank the people on my dissertation committee and other lab mates. Thank you.